Hello. Most of you have probably not actually seen my face or heard my voice, so allow me to introduce myself. I am Peter Harnish. I'm the laboratory manager for the physics department and the person teaching 170. So Lab 4 is watching this video. Frankly, it's material that is dry and a little dense, but things you need to hear. So instead of patronizingly making you go through exercises where you have to work through this, we're just going to talk for a few minutes, and hopefully you'll get everything you need out of that. So what we are talking about today is error and uncertainty, error analysis, error management, and designing an experiment. So let's go right into it. What is the difference between error and uncertainty? Well, first off, we need to define error. When I say error, I don't mean erroneous. It's not a mistake. Error is the discrepancies between our empirical data and what the model says it should happen. Nothing is wrong. It's just how much did we diverge from the ideal model. So with that in mind, what is the difference between error and uncertainty? Well, uncertainty is fuzziness. Every measurement has some amount of fuzziness to it because there's finite limits to what we can measure. Rulers can only get so small, so there will always be some little bit you don't know. You have calipers that go down to 1,000th of a meter. But do you know it down to 1,000,000th of a meter? No, there's an uncertainty, there's a fuzziness. So that's uncertainty. Error, on the other hand, is a problem with either data collection or agreement with data that can be dealt with in some way. You can fix error. So what are the kinds of error? You may have heard of these, right? So the first kind of error is systematic error. Systematic error is when the error is always part of the system. Your meter stick had the end sanded down a little bit, so now it's really only 99.5 centimeters. All your measurements are going to be off, but they're going to be off by an amount you know. Systematic error. Awesome. Random error is error that never repeats because the universe has uncertainty and there's craziness and maybe there was a breeze and maybe a truck was rattling outside and who knows, but it's a random error. The important thing there is that it never repeats, which means if you keep repeating the experiment, the error won't come with it. So you can overpower error analytically, mathematically, through repetition. Now there's one other kind of error that you may have heard of. You may have even cited it. Human error. What is human error? Human error is a euphemism for I messed up and I am too lazy or too busy or too late in my realization to do anything about it. Human error is an admission of guilt. So we have our three kinds of error. Then we have uncertainty. How do we deal with these? How do we manage them? Well, uncertainty, we just need better measurements. More measurements, better devices, and you get the uncertainty down. Systematic errors, we either need to fix it in engineering beforehand, get a new ruler that isn't broken, that kind of thing, or we can fix it after the fact using math. Random error, we can fix by just sheer numbers. If you repeat your measurement enough times, you will eventually have enough that statistically the random error will drop away. Your signal to noise ratio will get better, and your signal, your good measurement, will overcome that random error and become visible. Quick sidetrack before we talk about how to deal with these numbers. We have to talk about how we write them down. So first and foremost, you know them, you love them, significant figures. What's the deal with significant figures? Well, there are a lot of rules, and frankly, we as physicists don't care about most of them. Because here's why. Units are more important. That's most of it. They say leading zeros matter. So point, bunch of zeros, 1. How many significant figures is that? Well, I don't know. What are the units on it? If I measured in this decimal place here, it's 1, right? Who cares that it's 1 millionth, but I measured in 1 millionths? I measured in 1 billionths? Units. Units are what matter. So for the most part, sig figs, meh, blah, blah, we don't care. What we really care about, what happens instead of significant figures, is tolerances. Your plus or minus, that's what matters. So let's look at this number. Does that number make sense? No. No, that number does not. Why not? Well, if you only trust it by plus or minus this much, right? Do any of those decimals matter? No, they're in the fuzz. They're already gone. That's how we do sig figs here in science for the most part. It's those tolerances that actually set it up. They tell you what the deal is. More or less, those are the empirical equivalent of units. Your confidence level. Cool. The other thing we have to talk about this is rounding. How do you deal with rounding? Well, it's pretty easy. If the number is less than 5, you round down. If the number is greater than 5, you round up. And if the number is 5, you round to the nearest even value. Even value, where does that come from? Well, where it comes from is rounding down or rounding up. 5 is right in the middle. So if we always round 5 down, we're pulling all of our data down. If we always round 5 up, we're always pulling our data up. Now, you think that doesn't matter much, right? There's not a lot, right? We're only rounding the 0.5s. That's not a big deal. In real science, like super colliding science, like intergalactic science, right? Where we're taking terabytes of data per second. All those 0.5s add up real fast. So by rounding to the nearest even number, half the time we're going up, half the time we're going down, it all is going to work out, and we're not drifting our average up or down through rounding. Cool? Cool. So you've taken measurements, you have them written down. How do you now analyze those data to figure out what your uncertainty is, to figure out what that confidence level is? Well, we're going to talk about that in terms of sample size. How many individual measurements did you take? So the first case is n equals 1. One measurement. My confidence is plus or minus 1/2 the smallest unit on the meter. I know I'm closer to 9 than I am to 10 or 8, but it's rough. So we're going to say it's 9 plus or minus 1/2. For small data sets, let's say n is less than 1,000, we're going to use the small data set methods, which look like this. So the big things here that you'll notice, we have our average, great. We have our range, which is just like the whole range that is encompassed. And our uncertainty in a measurement is half that range. Cool. Now the uncertainty in the mean, in that average, looks a little bit funnier. It looks like this, right? We have that square root of n in there, which means our measured value is our average plus or minus our uncertainty in the mean. If we've done enough that we have a large data set, let's say n is greater than 100, then our data looks like this. So we still have average. It just has a sigma now because it's big. Bah. Uncertainty in the measurement. What's that? That's right, standard deviation. Well done. To get to uncertainty in the mean, we still have that square root of n. And finally, our measured value is our mean and our uncertainty in the mean. The two biggest things that you should have gotten from those tables are, 1, Why is it square root of n? Why do we have over square root of n? Because more data points help, but they only help so much, right? So that's where that square root comes in. There are diminishing returns by getting a large sample size. The other thing that's really important, which may have caught some of you, small numbers stop at 1,000 and large numbers start at 100. What about that range in the middle there? Well, that's up to you. You have to decide if your data is small or large. Now, I said 100 and 1,000 as rough numbers. What is the actual difference between small and big? Distribution. A large data set has a bell curve. We can assume that our data fits that bell curve, and because it fits that bell curve, we can use standard deviations. We can do things. Small data sets, there aren't enough data points to fill out that bell curve. So we have to do things in a more analytical method. But that's really what the difference is between those two. You might have noticed there was a lot of math there that I didn't talk about. You can go take a stats course. If you really want to know that math, that's fine. I don't need to teach you that math. You can look it up. Most importantly, those two tables I showed are just in manuals. You can look them up. I don't need to teach them to you. I don't need to derive them. I trust that you will know what the deal is. Cool? Cool. So we have those two methods, large numbers and small numbers. Both of those get you one measurement. They get you a data point. What if you need to combine these? We need to take multiple measurements and combine them together in some way of like length and height together become area? What's the uncertainty in that area? Well, there's an easy way to do this. In a most generalized sense, length, area, how do you combine things that are perpendicular? Quadrature, that's right. It's very Pythagorean in its methodology. I'm not going to go into most of it because, again, I don't need to teach you that math. It's fine. What's important is it looks like this. As you can see, there is a generalized version and then also subversions listed here for all the specifics. If you want to add, if you want to multiply, whatever. Again, this is a known table. I'm going to give you this table in a handout. You should be able to figure this out. Cool, cool. The next thing I want to talk to you about is curve fitting. Why it's useful, what it's good at, what it's bad at, where does its power lie. For that, I am going to actually turn this video over to someone who is much better at explaining curve fitting than me. And that's me from a while ago when the world was less on fire and my brain was a little bit better. Take it over. So you have your data. It's good, we trust it, you can clearly see trends in it. Now you need to figure out how that trend looks mathematically and if it's a good fit. Well, there are ways to see if your data fits, RMSE values, regressions, R-squared values, things like this. But the single most important thing is, does it make physical sense? And to do that, we need to look at the physics, not at the math. You can put almost any data you want in a graph and fit it with a 12th order polynomial. If you give me a high enough order polynomial, I can make the Philadelphia skyline. Doesn't mean it's good. We need to look at what that math actually means from a physics perspective. Let's look at an equation you already know. So we see a lot of letters here. We see a lot of numbers. Let's go ahead and strip it down to just its polynomial form. Now, looking at these values, something that I hope you can see. When we look at the polynomials, we have these coefficients. And if we compare the coefficients to the physics equation, each of those coefficients is a value we can also measure empirically. We can measure the starting position. We can measure the starting velocity. We can measure 1/2 the acceleration. That's how we know that this equation makes sense physically. Every coefficient in it is something we could measure independently. It is possible that the data you've collected, due to whatever reason, is better fit by a 5th order polynomial as opposed to a 3rd order polynomial. But can you measure what all those values should be? Do you know what all of those coefficients are? If you don't, maybe you're overfitting. What is overfitting? Overfitting is when you let the computer have too many knobs. If you give it a 7th order polynomial, it has 7 different coefficients that it can tweak and do whatever chicanery it wants to try to get the line to go through the dots. Because your computer doesn't know physics. It only knows connect the dots. So it can give you values that make no sense for being in the real world, because it doesn't know that. It just connects the dots. Beyond not knowing physics, the other thing that curve fitting is really bad at is exponents. Let me give you an example. Look at this curve. Is this an x squared curve? Is this an x to the 4th curve? Is this an x to the 8th curve? What is curve fitting good at? Well, curve fitting is very good at finding those exponents, and it's great at averagings. So that's really what we're doing when we're taking a slope. Sure, you could take your data point 1, calculate a value. 2, calculate a value. 3, calculate a value. Calculate all of those values, average them, you have your thing. But what if some of them are bad? What if some of them aren't good? They're in the averages as much as everything else. But if you graph them all and you take a slope, now you have a weighted average across all of your data. Outliers look like outliers, and you can get very precise calculations by taking a slope. Also, we as humans are very good at looking at shapes. We are not good at reading data tables. So it's often much, much easier to see a graph and understand what's going on and get insight into behavior than to look at a data table and try to find a trend. As I've said, the big problem with the computer trying to fit your physics data is that it doesn't know physics. But you know physics, or at least enough physics to help the computer along. So let's take a look at this equation. Right? This might be a thing that you play with. Maybe it's Hooke's law, maybe it's something else. But this equation makes some assumptions. What are they? Well, the two real big ones are that your value of x is perfect, but maybe it's not. We took this data, there could be some systematic error. Second, what is the value when x equals 0? That's right. But what if at x equals 0, y doesn't equal 0? What if there's some displacement there? What if there's some offset? If there's any amount of offset, and if x is at all not right, the computer is going to read this, and it's going to hate you, and it's going to put out garbage. But we know that these are problems, so we can fix them by instead using this equation. Now, what did we change here? Well, we added 2 fitting parameters. The first is that we've added this additional x term, right? That we now have x plus b. What is that plus b? That plus b is whatever we know to be the change in x. Maybe there's a calibration error there. Maybe we know that, maybe we just don't trust our sensors. And we know there could be an error. If our data is perfect, B could be 0 in our fit, and we'll be really proud of ourselves. But maybe it's not, and we can address that. The other one is that C at the end. That's our offset, our background, right? What if there's, whatever this Y is, what if there's always some of it present? That is now there in the C, and we can account for that. Another way that you could help the computer is by taking your equation that's difficult and making it into an equation that's less difficult for the computer. Because what do we know that computers are not great at? Curves. But what are computers good at? Straight lines. Straight lines are easy. They're so easy that your accounting software can do them. That's right, Excel is accounting software. So how do we make this into a straight line? Well, we could do something like this. Now, this value we're trying to get out isn't buried in a fraction, it's the slope. And finding the slope of data is easy. But we, as the physicists, had to make that an easy thing to find by rearranging this for the computer. If we want to go even further with this, we could use linearizing and fitting parameters to double check empirical measurements. So let's go back an equation and we'll start with this one. What if we want the computer to verify B and C for us? We have empirical values, but we're not sure if those are right. Well, what we can do in that case is pretty straightforward. We know what they are, we let the computer fit it, and we compare their values with our values. Great. What if we don't trust this equation? Like that exponent. What if we don't know if that's a 2? What if it could be a 3? What if it could be a 1? What if it could be a minus 1/2? Well, we know computers are bad at exponents, so we can't let it fit the exponent, but they're good at slopes. So how do you turn a slope into an exponent? That's right, the thing you never thought was actually going to be useful, logarithms. So if we take the log of both sides of this equation and then do a little bit of algebra to it, we get this. Now, if you look here, that exponent is now the slope. Caveat, very important here. In this fit, where do we get those values for B and C? We must use the empirical values that we measured by hand. Why can't we use the values that the computer gave us in that first fit? Because the computer will perform any sin necessary to get B and C to produce the exponent we gave it. So if we found B and C using an exponent of 2, it will perform anything necessary to guarantee the exponent's 2. So if we use those values to check the exponent, they're going to be 2, because that's what it was designed to do. So if we do this method, we must use empirical values that we have measured independently to verify that exponent. Thank you. Thank you, me, from much earlier in the lockdown. So, that's error analysis, curve fitting, data processing, all of that stuff. That's what you needed to hear about that. Let's move on to the much more interesting part of this, the part that I know that you were nervous about, the final project and how to do that well. How to design a project, how to design an experiment. So, first and foremost, you need to have a goal in mind. Now, what that goal is very, very important. What's also very important is what that goal is not. I think most of the time when these kinds of things go off the rail, it's because they have a goal that's unreasonable or not realistic. I am going to use physics to figure out everything about a ball. Okay? What about a ball? About its mass, about its density, about its chemical properties, about its material properties, about how it interacts with different surfaces. Is it interacting in a bouncing way, in a rolling way? Is it compressing? Is it not compressing? Is that temperature dependent? Is that pressure dependent? Blah, blah. Yes. That suddenly became, the entirety of your life is studying that ball. That's way too much. We're not interested in that. We're interested in studying a simple thing, a direct thing. So with that in mind, here are some kinds of thought exercises to work through to figure out how to do your problem. Can you simplify down to an idea? Can you take a three-dimensional activity and make it two-dimensional? Can you take a two-dimensional activity and make it one-dimensional? Can you make the event slower so you can see what's going on? Could you make the event repeatable so it happens the exact same way every time and you can study each of those repetitions? Could you study it more directly, right? Could you get studying only this little part of it by measuring specifically this? Would it make sense to build a toy of the real scenario? We call this a toy model, where we have kind of a simplified version of what we really want to play with. But by using the simplified version, it's simple enough that we can understand all of the moving parts. So that's the kind of thought process we need to go through when we're designing an experiment. We take the big question of what we find interesting, and we kind of pare it down and shape it until we get to little questions that we can answer. This little question, this little question, this little question, this little question. And once we have all those little chunks, we can start putting them back together until we get to the big question, right? So we need to think about these things when we're designing our experiments. And that's what your project is. It's an experiment that you're developing. That, of course, then leads to the question, what kind of experiments? What kind of projects? What is this final project that we need to be worried about? All right, here's the deal. Effectively, this final project is going to be you doing 3 to 4 labs worth of experimenting on a subject you find interesting. Now, that could go all over the place. That could be very quickly become chasing cats around. So we do have some structure to it. First, you are going to write a proposal. That proposal, you're going to turn into me, is going to be 1 to 2 pages, and it outlines what you want your project to be. Specifically, it's going to outline it in 3 different levels. The first is kind of an intro, gimme, I'm sure I could do this, right? Like, easy, spend an hour, I'm gonna bang that one out of the park, great. Second level is the real experiment. That's the bulk of what's going on, what you find interesting, what is going to be the good stuff. The third level is your bonus material. If it turns out that you're actually the genius that your parents have always told you you are, and you burn through all of this, what are you going to do? To phrase it another way, if I gave you an additional 2 weeks, what else could you have done? That's what that bonus stuff is. It's that extra stuff that would be very interesting, but is not going to be, that's above and beyond. That's that third level. For all 3 of these levels, you need to write up what you're going to do, how you're going to do it, what kind of equipment you need. There should be diagrams, that kind of thing. When I say diagrams, I don't mean blueprints. I don't mean artistic renderings. I mean a picture so that I can tell what your words mean, like a cartoon of what you're going to do. So when you say, I dropped it off the ramp, that could be like 70 different things, depending on the size of the ramp and what you're dropping and whatever. So you have a cartoon of like, oh, I'm dropping it off the ramp. Good. That's what we're looking for the proposal. I acknowledge some of you are probably going to write proposals that aren't going to work for various reasons. Be it that you're reaching too far, that is way too big of a project because you're ambitious and you want to go out and get it. And I don't want you burning out in November trying to get it. That's not the point here. It could be because it's too easy, because I know that's a thing that you can bang the whole project out in 2 hours, and that's low-hanging fruit. You're better than that. The third one, which I imagine is going to be the bulk of if there needs to be things to fix, are going to be things that I know won't work because I've done them, because I've played with those things, because I've tried to study those things, because I've used that equipment before and I know that you're going to run into trouble. So there are going to be revisions on proposals. Proposals could be straight, just given back to you like, great, have fun. They could be given back to you like, no, this is never going to work. New proposal, give me a new one. Or they could be given back to you with here's some rewrites. Let's do a round of revisions, see if that gets it there. That kind of thing. So that's going to be your proposals. You are then going to have the rest of November to work on those projects. I am not going to even pretend to imagine that this lab is a super high priority for you. I know what the deal is. I don't expect you to spend 3 weeks at the desk working on the project. I expect maybe 3 or 4 hours of work a week at most across November. So that's well within the range of like, I'm going to spend all of one Thursday working on this, and then I'm not going to touch it for 2 weeks. That's fine. You know your schedule way better than I know your schedule. The only thing is that you can't put it all off to the end. So, to make sure that doesn't happen, you are going to have a progress report in the middle of this project. That progress report is not a rough draft. It's not your presentation, but light. It's you checking in with me, writing a page up. Hey, here's where I am. This stuff is working. I'm feeling good about this. I'm not feeling good about this. Do you have any notes about this? I know we said we were going to do this, but that's looking a little iffy. Do you have any ideas? Like, just a progress report, checking in with me to make sure you haven't blown all of it off, to make sure that you're not out in the weeds and lost, that kind of thing. Then, at the end, you are going to write, as your final report, a presentation. So at the end of all of this, you're going to do a presentation about your project. I am saying presentation, not a report. You are going to make a video and submit it. Now, when I say a video, I don't mean like an hour documentary. I mean, this is the kind of thing that would be a 5-minute slideshow presentation if we were in the same room. But it's not. We're not in the same room. So you're going to make a video so that the other people in the lab can watch your presentation. That's what it's going to be. Because I know that some of you, hopefully most of you, all of you would be great, are going to do some really interesting, cool stuff that it would be great if everyone could see. So for your final report, you're going to make a presentation on the order of a 5 to 10 minute slideshow kind of talk. Maybe with videos, maybe with pictures. We're going to talk about it a lot more later. And that's going to be your project at the end. You're going to submit a report that everyone will get to watch. Hopefully, now that you've heard that, this is going to be a lot less scary. Hopefully. So the final question on this then, what kind of projects am I expecting? What am I expecting you to do? Well, let me give you some examples of the kinds of projects that have worked in the past. We have interesting little bits of physics, like the moment when a sliding thing starts to roll, or the moment when a balanced thing becomes unbalanced on its own. Little bits of physics that are interesting that you can study. Or you could study basics of material science. Things like a non-Newtonian fluid, things like a coefficient of friction, things like the elastic properties of a polymer or a rubber band or things like that. And the last one, which I think often ends up being some of the interesting stuff, no pressure, but doing a detailed examination of something cool, like a double pendulum, or a rattleback, or one of those like wind-up cars going up a hill. And what happens is it loses its steam from the wind and the hill and the friction and the, like, just getting into that and like figuring out that nitty-gritty stuff I think is really interesting and can lead to some very cool projects. Now, what tools do you have to do this? Well, everything that we've done so far. Looking behind the curtain, the reason you've done these 3 previous labs was to teach you how to use those tools. By now, you should be good at video analysis. By now, you should understand how to use accelerations if you have an accelerometer. You should understand how to use multiple methods to study the same thing. You should understand how calculated columns work. You should understand how to do energy analyses. All of those labs, the reason I made you do them wasn't to make you more comfortable with projectile motion. Dr. Johnson should have handled that. They were to give you these tools that you could now study something you find interesting. That's what I want this final project to be. You having a reason to play with physics for a couple of weeks, to find something that you think is interesting and you want to put some time into to work out. That's what I really hope. So, there was a lot of boring things in that. I would like to give another thank you to me from much earlier in the lockdown for giving that explanation of curve fitting. And I hope this answered a lot of questions, and I hope it quelled a lot of fears for what we're expecting out of this final project. I'm really looking forward to seeing what you all come up with. Please do not hesitate to talk to me, to send me emails in Canvas or, through the normal emails, whatever. You are not an island. You are not in a vacuum. I am here to work with you on all of this, and I want to see what you come up with. I'm really looking forward to it. Yeah, so I think that is Lab 4, I guess. Hopefully, I'll talk to you all soon. Bye.